Hello everyone. Today we are going to give our final presentation. Our presentation includes 4 parts. First, let me introduce the background and basic ideas of our project. Driver monitoring system has been developed by many manufacturers in purpose of achieving a higher driving safety. A driving monitoring system, DMS, uses a camera to monitor driver alertness that not only recognizes the driver but also checks his or her level of alertness. Its purpose is to adjust the driver's emotion states and keep him or her focused on driving. In addition, it can be used to prevent sleepy driving and distracted driving. For the expression detection, it's a process of identifying human emotions. It combines the technology of face detection and emotion extraction. Currently, it has been applied in many situations. Here, for our project, we want to combine the ideas of DMS and emotion detection and developed a real-time system that can track the driver's emotions and attention continuously. Here, in the past semester, we focused on data preprocessing, emotion model building, and improvements, drowsiness detection, and head position estimation. For the emotion detection model, we used 3 datasets. FER dataset has the large number of images, while the CK Plus has a more accurate label annotation. For the last dataset, it is the only one used in real driving environment. They are combined and serve as training source. For the test part, as most of the papers evaluate their algorithm based on the Kaggle context using the FER dataset. To make a comparison, we used the same testing data. We have 5 steps in data preparation. We use data cleaning to erase the wrong faces. Then we do data transformation to make all the images consistent with each other. Then we did face extraction and feature annotation. The final output is actually a combination of 3 parts. First is the images. Others are the landmarks and HOG features in tuple form. For the model design, we come up with 3 ideas. The first is a convolutional neural networks with 3 hidden pooling layers. The second is a transfer learning model based on VGG16. We added another convolutional layer at the bottom to extend the grayscale images into 3 channels. In addition, we designed a multi-input model to include the features into training. We trained the images by CNN. In the meanwhile, we added 2 fully connected layers to transfer the other features. Then we concatenate them, use another dense layer as the output. Based on different models, we conducted a series of experiments to test the model's quality. In the beginning, we don't use the additional features, using the images as the only input. This is the only difference lies in the choice of model. And the result shows that the CNN model performs much better than the transfer learning one. Its main weakness is its detection for fear and disgust. Then we include the other 2 features. The resulting accuracy is also around 60%. Compared with not using additional features, the new models has a better performance in detecting disgust and fear. In the experiment process, we found 2 problems. First is that the model is too large. So we want to reduce the image size. We proposed a new data augmentation method. We cropped the original images to the size of 42. It is randomly repeated for 10 times, and all the cropped images are used in training. The other problem is that the test data cannot be augmented. So Its prediction is quite limited. As a result, we want to use multiply prediction based on measure vote and averaging method. Finally, we do some new experiments and compare them with previous ones. The base models has an accuracy of about 70%, and from this graph you can see its performance has been prior to human naked eyes. To further enrich the functions of our system so that we can monitor the driver's states better, we developed two extension modules, the drowsiness detection and distraction monitoring. For drowsiness detection, we aim to compute eye aspect ratio, EAR, and when it's constant and stable, it means open eyes. If there is a blink, the value will decrease sharply to 0, and if the eyes are closed, EAR will become also constant, but much smaller. The equations below are the EAR formula. We use OpenCV to extract facial landmarks and then calculate the EAR values. For the algorithm, we use a threshold equal to 0.24, and if the value less than that and lasts for more than 1 second, the voice alarm will be triggered saying that please wake up, and other situations means normal states. The following charts are the results of normal states, which are regular and stable, and the sleepy states of which values are smaller but not stable. For distraction monitoring, we aim to project the landmarks on the image into the camera matrix with 3D points. With the pitch and yaw extent, we can decide if the head position is frontal or not. We use OpenCV solve PNP method to calculate the rotation vector and the transition vector. Then we use the project points method to compute the yaw and pitch values. We have set the thresholds as the following. Considering the drivers will also look around when driving to observe the roads, but this won't be too long, so we set the lasting time should be within 60 frames. When the thresholds are crossed for more than 60 frames, the voice alarm will be triggered saying that please look straight, and other situations are normal. Next is the real-time system demo. This is our system architecture. Considering sometimes if the camera is not set in a suitable place with the right angle, the camera cannot capture the face parts. If the face are not detected, we also set the voice alarm saying that please align the camera. Then the landmark and face detectors will get the corresponding coordinates, and the according thresholds are crossed for a certain period. There will be voice alarm. If the driver is not sleepy and not distracted, we then to detect his emotional states. The cropped face will be processed into grayscale and resized. Then the emotion classifier will predict the label. Here are the two demos we recorded. On the right side of the screen are the landmarks mask of my face. The cube represented the projected 3D coordinates, which visualized the yaw and pitch angles. The bottom are the three values computed in time. First, I make happy and surprised expressions, and then I closed my eyes to show a sleepy state.
Please don't sleep.
Then the voice alarm is triggered. When I look
Please
around,
look straight.
there's also a voice alarm. Then I made different expressions.
Please don't sleep.
If I left the screen, there will be a voice reminding me of aligning the camera.
Please align the camera.
The next demo is about the real driving environment. The driver's expressions can be analyzed in time, and when he looks around, there also be a voice alarm.
Please look straight. Please look straight.
The real-time system combining three main modules, emotion recognition, drowsiness detection, and distraction monitoring, helps drivers to stay in a safe driving state. The emotion classifier is relatively accurate on happy, surprised, sad, and angry, but can make mistakes on other subtle expressions. Drowsiness detection and distraction detection modules performs very well, and both provide voice alarms. To better help drivers to stay in a safe state when driving, there are also some improvements we can do for future work. First, we can combine the real-time data from vehicles like the speed, accelerate velocity, and brake with facial data. This can better analyze the driver states. To better release the negative emotions of drivers, this real-time system can be attached to the in-vehicle systems to play relaxed music or choose radio stations accordingly. These are the improvements we can do for future. Thank you. That's all.